Good evening, everyone. Welcome to this Foundation Engineering class. This is the last class of our NPTEL course, of this NPTEL course, and it is extra class of this course. We already covered 12-week class, TA classes, and this is the last class of this Foundation Engineering course. And in this class, I am discussing the previous class very briefly, very short, and try to give some inputs on the upcoming exam to solve some very important problems. So let's start our today's session. So first of all, I introduce myself. So good evening, everyone. My name is Rajat Bonik. I am from IIT Sambhanga, and I am one of the PMRF research scholar at IITSM Dhanbad and also a teaching assistant of this course, Foundation Engineering, which is conducted by Professor Dilip Kumar Vaidya. I have also 6 month teaching experience in as a TA in NPTEL. My previous course was ground improvement and which also conducted by Professor Dilip Kumar Vaidya. So today is the last class of our NPTEL 12 NPTEL. We already covered 12 classes of this regarding this course, and which includes 60 lectures. And in today's class, I am just discussing the previous lectures very briefly. Before starting the previous lectures, today's session, I want to some make give some 2 or 3 points that this session is recorded and it will be uploaded my YouTube channel. Also, whatever I am discussing, if any extra, it will be uploaded to my Google Drive. And also, one thing that if my network, if there is any network issue or I am disconnected, please don't worry. I will try to solve this problem and rejoin the meeting again. So, so before starting the previous classes, I think yesterday 2 lectures are remaining. First, we uh, complete these 2 lectures, lecture number 59 and 60. Then we discuss all the classes, all the 12 classes very briefly. Whatever I am discussing in these classes, very briefly I am discussing, and also uh, I uh, I am showing some important problems regarding these classes through some reputed books. So please stay on the meeting. So let's start our today's session. So this session is also 2 hour session. So let's start. I'm sharing my screen. Please wait. I think the slides are visible to everyone. Also, my audio is clear. So let's start. Mm, in previous class, we discuss about the machine foundation. So it is the continuation of this machine foundation. This lecture number 59. So in previous class we solved some numerical problem on machine foundation, also on dynamic links of foundation. So where we study the different types of vibration, free vibration, for vibration, also in that undamped system, damped system, when they are equation, numerical form like that, and also see the how to find damping ratio by different method like half bandwidth method or logarithmic decrement method like that, and solve some very important or logical problems. And this 15 number lecture is only belongs to theory. There is no numerical. So in first slide, it is discuss about the different types of machine foundation. So it is here it is categorized in four way. That is foundation for impact producing machine. That means only impact load is applied to the foundation as a dynamic load. And then foundation for machine producing periodical force. That means a machine have a rotating mass which produce the periodic load with the time, which also a dynamic, also a type of dynamic load. So that is one type. Then machine for high speed machinery. So the if rotating mass speed is increased, it is called high speed machinery. So this is also one type, and there is another type which is miscellaneous. Then these types of machine as suggested foundation. For this type of machine, what type of foundation we need, what type and what shape of foundation we need, we now discuss in this slide. So the machine producing impulse force, they suggested that the foundation should be block type foundation. And this foundation, this block type foundation is suitable for the machine which is include hammer, presses like that. Impulse force means the impact load. So for this we best and these force are generated by hammering or pressing. So for this block type of foundation is very suitable. Then a rotating type machine with low to medium frequency, they suggested that block type foundation with large contact area. Uh, uh, Large contact area. So this and this rotating type machines, rotating machine with low to medium frequency examples are large reciprocating engine, compressor, large blower like that. This so for this we use block type foundation with large contact area. So because it so then a read type machine with medium to high frequency. So for this, they suggested that foundation of block type. Foundation suggested that block type foundation resting on suitable elastic pad or spring. And the example for this rotating type machine with medium to high frequencies are medium size reciprocating engine, diesel engine, and gas engine. So for this rotating type machine with medium to high frequency, we use block type foundation resting on suitable elastic pad or spring. Then uh, rotating type with very high frequency, For this we use framed. For this we use uh, framed foundation or massive block with minimum contact area. And the example for this are for this rotating type with very high frequency is internal combustion engine, electric motor engine, and turbo generator. So for this type of machine, we use framed foundation or massive block with the minimum contact area. Then there is a shape of different type of block foundation. The block foundation is solid area and block hollow block foundation. So we either use this type or this type. If we use this type, it is the mass of this foundation is more than this type of foundation, but we need it to maintain the mass but increase the contact area. Then we use this hollow block foundation. Then there is the frame type foundation. You see, there is a frame structure by which the load is transferred to the ground surface. This is also one type of frame foundation. Then hammer foundation. So this hammer type of foundation, this is the arrangement of the hammer. So this is continuous to go down and up, and it is creating an impact load here. So for this registration, we use the block type foundation below. So this is the hammer foundation. And then rotating mass machine. So for this, we use also block type foundation, and for this we want to find out the dynamics property response. So we use this equation. We also go through this. This is nothing but the forced damped vibration equation, and this is the arrangement. This whole thing are arranged in this way, in a simpler way. This rotating mass is with the total mass of the foundation is represented as the solid blocks, and the stiffness and damping of the foundation is represented as spring and disperse system. We also discussed this. Then there is one table for defining types of soil, define what is the damping ratio. So it is said that the for dry before going to this, here it is given that there is used two types of loading. One is constant force loading with the time dependent. There another is a rotating mass loading frequency dependent. So for this, we for two types of we also find out the two different response of the foundation. Then, if we for dry sand and gravel, dry sand or gravel, the damping ratio is in between point zero 0.03 to 0.07, or we can say 3 to 7%. Oh, sorry, this is already in percent, so we say the 0.03 to 0.07%, and this is taken from the source Weissman and Hart in 1961. And these also different scientists given their literature for different types of damping ratio for different types of soil. This then dry and saturated sand, the damping ratio is in between zero point 0.01 to 0.03. For dry sand, it is zero point 0.03. For dry and saturated sand and gravel, it is in between zero point 0.05 to zero point 0.06. For clay, it is in between zero point 0.02 to zero point 0.05. For silty sand, it is in between zero point 0.03 to zero point 0.1. For dry sand, it is in between zero point 0.01 to 0.03%. So please go through this table for when you designing in the foundation for different types of soil to identify or measure the damping ratio for the foundation. Then there is analysis, different types of analysis, and for different types of analysis, what are the factors required for this type of analysis? So for analysis, approximate estimate for resonant frequency, the main factor are K and M, because with the help of K and M we find out our natural frequency. So the resonant frequency is that type of frequency which matches with our natural frequency. So the more important factor are K and M for this type of analysis. And K is here stiffness of the foundation, M is the mass of the foundation. Then if the analysis approximate estimate for motion at the frequencies while wave from the resonance, that means if the frequency is A from the resonant, that means either it is greater than from the resonant frequency or it is less than the resonant frequency. So if it is greater than the sorry, if the frequency or if the working frequency is less than the resonant frequency, then the most important factor is K, that is stiffness of the foundation. If it is A from the resonant frequency, or we can say greater than from the resonant frequency. Then most important factor is M, that is mass of the foundation. So, so, so why so? So you see that is, we know that omega proportional to F. So and also proportional to K by M. So proportional to K inversely proportional to M. So if it is less, frequency is less, that means if we need the frequency is less or very sensitive, then our stiffness should be very less. That's why then only the oscillation is happen. If our frequency is very more, we need the system should be stable, and then we should increase the mass of the foundation. So this is the reason. Then upper limit for motion, if our analysis is upper limit for motion at the frequencies near the resonant frequency, then we use D, K, and M as our uh, factor, design factor. D is the damping ratio, K is the stiffness of the foundation, and M is the mass of the foundation. So why it is so we know that U is equal to for constant force F naught by K root over 1 minus omega by omega n whole square plus 2d omega by omega n whole square. So you see that this response of the system, damping force vibration system, is depend on the K, also depend on the omega of the system, also depend on the natural frequency, or indirectly we can say root over K by N. So for our designing for upper limit of a motion at the frequency near the resonance, that means at resonance we know that frequency is 1 by d omega square, or magnification factor is 1 by 2d root over 1 minus d square. Then so we see that this equation is requires the d. So we see for so our measure design factors are d and k, or sometimes the mass for this analysis. So this is that's it. The completion of the foundation, machine foundation. So now this is the completion of our course. Till up to this is the syllabus of this Nptel course. Now I am discussing The total summary of this course in lecture number 60. After that, we try to solve or discuss the book example problem for the important example problem for this course. So move on to the lecture number 60, which is the summary of the total course. We already just in read out these slides. So please uh, try to understand. Then, so this first slide, it is said that the soil mechanics is the tool that help you select, design, construct foundation elements and earth structure. So it is true. So based on the soil mechanics, we actually in this course, foundation in course, we studied the advanced soil mechanics. So the basic soil mechanics are where we studied the void ratio, permeability, and then shear strength parameter like that. So by this, with the help of the soil mechanics tool, we actually mainly design the foundation element and different earth structure. Earth structures like sheet pile, retaining wall, dam, like that. These are the embankment. These are the major earth structure in our day-to-day life, or bridges like that. Then failure is an unexpected difference between the expected and observed behavior. The key goal as a foundation engineering build economic foundation that works safe and serviceable. So the main important thing for the foundation engineering, not to build just the foundation, but also it should be very safe, economic, and serviceable. Safe means it is safe from uh, bearing capacity failure or shear failure of the soil like that, and serviceable means it should be settled within the permissible settlement limit, and economic in the sense that by choosing the different types of foundation for different types of soil. So if our soil is very good condition and the bearing capacity is very high, and or we can say it is in the rocky ground, then there is no use for the pile foundation or any other deep foundation. So we easily go for the shallow type foundation, which is very economical to cost effective for the deep foundation. Then build with confidence. So it actually it is said that it is built with confidence. That means use field work, lab result, analysis, design, but at the end use what work. So that means uh, for this safe and serviceable foundation, we use some field work. We go for some field work, also go for some laboratory testing, and analysis the result, and design the foundation. And but it is not the whole thing. At the end, we use the some expert opinion on that type of uh, uh, soil also. Then understand the ultimate bearing capacity. So in this course, in very beginning, we study the shallow foundation. In shallow foundation, we study the ultimate bearing capacity theories, um, which is given by Sturgeon, Mayerhoff, like that. And Tajagi is the one which is who give the fast bearing capacity formula based on the steep footing. So and they are also maintain some assumption to find out this bearing capacity formula. Then this bearing capacity formula is modified by different types of different scientists, researchers like Mayerov is which Mayerov, and also in this bearing capacity formula we study the different types of bearing capacity factor NC and gamma and phi, which is depend on the soil phi of the soil. We study all of this. Then we also understand the net ultimate bearing capacity, safe ultimate bearing capacity, and finally allowable bearing capacity also. So net ultimate bearing capacity is nothing but the ultimate bearing capacity minus self weight of the soil up to the depth of the foundation. That means minus gamma df. And safe ultimate bearing capacity is that if we divide this net ultimate bearing capacity with the factor of safety, then added again the self weight of the soil up to depth of the foundation, then it will give the safe ultimate bearing capacity. And there is a one term allowable bearing capacity. So you remember that allowable bearing capacity is not equal to the safe bearing capacity. So allowable bearing capacity is that type of bearing capacity which is safe from not only safe from the shear failure of the soil but also safe from the settlement of the soil. So this bearing capacity is called allowable bearing capacity. Then we study the bearing capacity for different types of soil. So that means for pure sand, for pure clay, we know that for pure clay the cohesion term is only remaining. The phi term, that means half n gamma b n q, sorry, n half gamma b n gamma is neglected because n gamma is equal to 0 for pure clay, uh, and for pure sand the cohesion of the soil is equal to 0, so also the cohesion part is neglected, which is very useful for finding out the bearing capacity for different types of soil condition. Then we also studied the effect of water table on the bearing capacity. We know that water reduce the bearing capacity of the soil due to the buoyancy effect, and this buoyancy effect is denoted by the submerged unit weight of the soil. So we know that the submerged unit weight is the gamma saturated minus gamma W. Uh, so you see that it is already reducing the bearing unit weight of the soil, so automatically reducing the bearing capacity of the soil. Then effect of the depth of embedment, that is depth factor, shape factor, load inclination of the bearing capacity. We studied that means the DI, DC, uh, DQ. We all of this we go through, and this depth factor, shape factor, and inclination factor is given by the mayor of and it you can go through it. There is a different equation for this depth factor, shape factor, and inclination factor, and this Mayorov equation also used in our IS code also. This Indian Standard Code to find out the bearing capacity of the shallow foundation. Also, we use this equation, Mayorov equation. Then we also studied the bearing capacity on eccentric loaded footing. We know that if the loading is eccentrically loaded on the footing, that means it is not lie on the CG of the foundation, away from the CG like this. Then we the effective area of the foundation is reduced due to the eccentricity. So we also studied this type of problem. So please go through it. Like the if you say the our load is at this area, then the effective on this point, then the effective area of this foundation is this only, because we neglect this, and the effective width is P minus 2. Please remember this. E is the eccentricity of the loading from the CG. Then We go through the different types of settlement of for shallow foundation. That is the elastic settlement, consolidation settlement. In consolidation settlement, there are two types: primary consolidation settlement and secondary consolidation settlement. And also find the different method to estimate the elastic settlement. Also, and then there is a different method we also go through to find out the consideration settlement, whether it is normally consolidated or whether it is over consolidated side. And this to find out this elastic consideration settlement, we use the consolidation of the soil which is settlement consolidation settlement of the soil, that is del H is equal to H into CC. CC is the coefficient of compression index, and the 1 plus E log 10 uh, sigma dash plus del sigma into sigma v dash only vertical stress. So where sigma v dash is the vertical stress and del sigma is the change in pressure due to the construction of the or increment of pressure due to the construction of the foundation. E is the void ratio, H is the thickness of the layer, clay layer where we find the concentration settlement. Again, CC is belongs CC is depends on the liquid limit of the soil, and it is given that 0.009, I think, WL minus 10 or 10, I think. Please check once this formula or go through it. And this elastic settlement of the foundation is depend on the Hooke's law, which is equal to QS into B by ES 1 minus mu square into IF. I is the influence factor. Mu is the uh, Poisson ratio of the soil. B is the width of the foundation. ES is the modulus of the soil. And QS is the pressure coming from the foundation due to the loading on the foundation. Then we study the time rate of the consolidation, degree of the consolidation, or case of single or double drainage. So we that means time rate consolidation means we this consolidation depends on the time, and it is depends on the time factor, that is TV is CV into H square. H is the drainage path, T is the time, CV is the consolidation coefficient, and this H is depend on the drainage system, whether it is single drainage or double drainage. For single drainage, it is H is equal to uh, thickness of the foundation, sorry, thickness of the layer, clay layer, and for double drainage, this H is equal to the half of the thickness of the clay layer. How we find out the consolidation? Then we study the different types of exploration of the soil to find out the properties of the soil, whether properties like engineering properties, characteristics like that. And here we study the SPT, CPT, then which are the non-destructive tests, and also study the different types of sampler used to collect the sampler, Shelby, tube, like that. And we study the different ratio like area ratio, clearance ratio, which is help to design this sampler for extracting the non undisturbed sample from the ground, like that. Then also find out the number of boreholes required for this for specific type of soil locations, and also study the spacing between this borehole and depth of the borehole. And we also study the different type of field test to find out this soil property, and also study the different types of laboratory tests to find out this too. In field test, these are SPT tests, CPT tests. In laboratory tests, either vane shear test mostly used to find out the soil property, or compaction test like shallow, sorry, Standard Proctor test or modified Proctor test we mostly use. Then we also study the different types of retaining wall used to retain the earth soil uh, of the embankment, whether it is embankment of a road uh, or it is on the slope. To we design this type of retaining wall also, and this retaining wall is depend on the designing of this retaining wall and depend on the earth pressure of different types of earth pressure of the soil, and there is three types of earth pressure at rest, active earth pressure, passive earth pressure. So we also study find the one diagram that define the magnitude of different types of earth pressure. So we see that earth pressure, active earth pressure, is less than the earth pressure at rest, less than the passive earth pressure. So the earth pressure, a passive case, the earth pressure is more than the all of the cases, and due to this pressure, force is generated and which is extracted on the retaining wall, uh, applied on the retaining wall, and we have to design the retaining in such a way that it should be carried or saved from this type of earth pressure, or saved from different types of loading which is developed by this type of earth pressure, like overturning, sliding, bearing capacity failure, like that we have to design. Then we also study the earth pressure theories, whether it is Rankine or Coulomb theories. So in Rankine theory, the common thing is that the surface of the retaining wall should be smooth, but in Coulomb we use the friction on the surface of the retaining wall. Then we study the level, slope, level, ground, backfill, also slope backfill. So in slope backfill, the difference is that the formula of the earth pressure theory coefficient is little bit changed, and it is included the angle of inclination of this slope backfill. That means if you say the surface of the backfill is inclined at an angle of beta, it it is impacted the on the formula of the coefficient of earth pressure. Normally, the coefficient of earth pressure of active case is 1 minus sine phi by 1 plus sine phi. So it will be modified and include the angle of beta with the help of cosine. So it is, I think, cos beta minus root over cos square beta minus cos square phi divided by cos beta plus root over cos square beta minus cos square phi into cos beta. I think it is for the active earth pressure case. If the slope, if the backfill is at the slope with the angle of beta, then we find out the earth pressure for different types of soil also, whether it is purely cohesive or purely cohesionless soil. Most of the case, the retaining wall is designed for the cohesionless soil because there is chance in cohesionless soil, loose cohesionless soil, where the angle of internal friction is very less, which may create the failure of the slope. So for this, most of the case we use the retaining wall, and also sometimes we use this retaining wall for layered backfill soil also. Then we studied the depth of the tension crack and depth of the unsupported excavation. And this case is for C5 soil, where C cohesion and also present an angle of internal friction of the soil, that is sandy nature of the soil also present. And where we find that depth of the tension K is 2C divided by gamma into root over K, and for a depth of unsupported, it is a 2 times of the tension K, which is equal to 4C divided by gamma into root over K. So please go through it once, which is helpful for you exam purpose. Then we also studied the stability of the slope or stability analysis against sliding, overturning, and bearing capacity, where we find out the factor of safety against sliding, which is greater than 1.5, factor of safety overturning, which is greater than 2, I think, and bearing capacity failure. Bearing capacity failure means safety means the bearing capacity or uh, vertical force uh, due to the arrangement of the retaining wall should be uh, which is in the vertical direction and should be retained or should be less than the bearing capacity of the soil. So there, then only the retaining wall is safe from the failure. And one thing that due to this vertical stress which is created due to this arrangement of this earth pressure, it should be within the uh, V by 6 distance from the middle of the retaining wall or center of the retaining wall, so that it should not create any tension crack in the base of the retaining wall. If it is greater than the B by 6 of the B by 6 means width of the foundation, B is the width of the foundation. So B by 6 width of the retaining wall. So if it is greater than B by 6, there may be possible due to the stress arrangement, there may be possible to create some tension on the at the base of the retaining wall, which is very dangerous for soil, because soil is weak in tension and there may be failure of the retaining wall. Then we go through the different types of deep foundation. In the deep foundation, we mostly study the pile foundation. So here we study the different types of pile plus based on the material, function, like that, and also the selection criteria. Then we study the load transfer mechanism of this pile foundation through friction or end bearing, and also find out the capacity of the single pile driven in the cohesive soil. For cohesive soil, the friction capacity of the pile is alpha C pi dl, average C bar pi dl. C bar is the average cohesion of the along the soil. Um, and for alpha is the addition factor, pi is D is the diameter of the pile, L is the length of the pile, and for cohesive soil, and bearing capacity is 9C pi by 4 d square. Uh, so by these two formula, we easily find out the load transfer mechanism of the for friction and bearing pile in cohesive soil. Then we also studied the capacity of the single pile driven in sand. For this case, we find out that K sigma B, the friction capacity is K sigma B 10 delta pi dl, where delta is the two-third of friction between the wall and soil, which is equal to the two-third of phi internal friction of the soil, and sigma v is the vertical average vertical stress along the pile length, and k is the coefficient of earth pressure for in active case, or either it is rest or in passive case, like that. And for n bearing case, the load is n bearing case in if the pile is in sand, the load is nq into q pi by 4 d square. Q is nothing but the gamma df, or we can say sigma v particle stress at the base of the, or at the pile base. Anchor is the bearing capacity factor, which is depend on the angle of internal friction of the soil. So by these two formula, we easily find out the bearing capacity or capacity of the single pile given in the cell. Then we also study the group capacity uh, of the piles, and also find out the efficiency of in the group of this file. Then we study the test of different test pile load test, which is helpful of, or these are the field tests, which is helpful for directly find out the capacity, pile capacity for the real field condition in this situation. Then we study the different types of settlement of the pile, and single pile and group pile. Either it is elastic settlement or it is concentration settlement. In elastic settlement, the settlement is occur in three way. The settlement along the length of the pile due to the pile material, the settlement surrounding the pile due to the friction on the pile, and settlement at the base of the pile due to the end bearing load. And for finding out the consolidation settlement, a plastic settlement, we use the consolidation formula in the pile group, and at a distance from 2/3 of h L from the surface of ground surface, or uh, from the pile cap. Then we study the different another different types of deformation, which is useful for retaining the soil structure, which is which are sheet pile wall, cantilever and anchor sheet pile wall, and estimate the depth of embedment of this cantilever sheet pile wall by rigorous method, and also by simplified method. Also find the depth of embedment for anchor pile, and also find out the anchor force for this anchor sheet pile. And today also we discuss this again very briefly in our later part. Then we study the deep excavation, which is mostly for this we mostly use the strut system, also base system, which is used to uh, stabilize the soil in this excavation or retain the surrounding area wall in the deep excavation to avoid collapse, and also study the bottom stability of this base excavation or deep excavation, and find out the maximum unsupported depth of this excavation, which is related to the tension track of the soil, or earth pressure for C5 soil in a passive case, sorry, active case. I will find out that the unsupported depth is 4C gamma root over Ka. Then in the last two classes, we go through the dynamics of the foundation, or dynamics of the machine foundation. So here we study the types of dynamic load, different types of dynamic load, different types of dynamic analysis, and equation of motion, different equation of motion for this type of load. Sorry, define equation for define dynamic loading. Here we study the free vibration, forced vibration. In free vibration, there are also two types: damped, undamped free vibration and damped free vibration. Also, forced vibration also we study undamped forced vibration or damped forced vibration. We also go through the different equation, mathematical equation for this for different types of vibration and solve the equation and find out the response of the soil for this type of vibration and find out the modes of the vibration and equation of motion of this vibration, natural frequency, and resonant amplitude. We also find out natural frequency is nothing but the root over omega is equal to root over k by m. Resonant frequency is this frequency which matches with the natural frequency. Due to this, the amplitude of the motion is suddenly increased, and this is called the resonant amplitude. Then again, we find out the estimation of the vibration amplitude for steady state vibration. Then we study the dynamic soil properties to find out the dynamic properties of the soil. Uh, ho- find out the damping of the soil, shear modulus of the soil, and also find out study the different method to find out the damping, like logarithmic increment method, half bandwidth method to find out the damping, and also study the overtone and undertone of the design. And these are the summaries of our total classes in this lecture number 60. And now, in our next 1 hour, we discuss some book example problem regarding the pile roof foundation and sheet pile, anchor pile, and brace excavation. So these are the example problem of reputed books. I mostly use the BNS Murthy. So please follow this type of books to solve the problem I'm also discussing here. So before going to that, I am taking now a small break uh, of 5 minutes. After that, we start again to solve the example problems or go through the example problems for these books. So please stay on the line. I am joining again after uh, 5 minutes. And stop my sharing. Please wait. I will join after 5 minutes. Welcome to this session again. So now we discuss some book example problem from some reputed books of foundation engineering. So let's start our session again. Uh, I'm sharing my screen again. Please stay on the line. I think it is visible to everyone. So there is so first problem is for single pile foundation. So it is given and concrete pile is driven to the medium dense to dense sand and diameter of pile is given in 12 inches. Uh, its embedded length is given 20 feet and also given the soil condition which is shown in the figure. Gamma is about 128 a pound per foot cube. Phi is 38 degree. K is zero point 0.9. K is the active earth pressure coefficient or earth pressure coefficient just. And said that no groundwater was encountered and the groundwater table is not expected to rise the life of the structure. So yeah, uh, pile capacity. The factor of safety is taken to find out the pile capacity. To factor of safety taken is 2. Uh, then now the solution. First, find out the critical depth. We know that the critical depth at which after which the vertical stress remain constant. So to find out the critical depth for dense sand, it is the 20 times of the pile diameter, which is equal to the 20 into the 1 feet. Pile diameter is given 12 inches. 12 inches is nothing but the 1 feet. So it is equal to 20 feet. So our calculation is divided in two ways. Uh, so our total length of the uh, pile is 20 feet. So our calculation is divided to a up to 20 feet and then remaining 5 feet. So first to find out the ultimate bearing capacity, which is divided in two forms. One is skin friction related, another one is and bearing related. So for King's fiction, where we use this the concept, critical depth concept, to find out the critical depth concept, first we draw the critical pressure diagram. So this pressure diagram is look like initially increasing after a depth of 20 feet, it is remain constant, and this pressure at 20 feet it is same as the pressure at the 25th feet, and this is why um, there is no order table is present, so this there is no change in effective stress. Total pressure is equal to the effective pressure. Then, so so to find the uh, friction force or friction capacity of this pipe, we actually find out the area of this pressure diagram up to 20 feet. So we divide this area from here to here, one area, here to here is one area. So it is a triangular shape, so we use the triangular formula. It is a rectangular shape, so we use rectangular formula. So you see that it is half 2560 lb, so it is pound per foot square. That means it is the base is 2560, height is 20, so half into 20 into 2560, then plus 2560 into 25 minus 20. So it is given as uh, 38400. Then K is given in the question, and we have to find out the delta. Delta normally, if it is not given, then we take two-thirds of the phi. Phi is the angle of internal friction, but here it is given 0.45. So use this. So formula is K sigma V 10 delta pi dl. So the answer is so you have to multiply this, put all this value here to get the answer. So this is 51500. Then you have to find out the Q tip resistance, that means end bearing resistance, or which is equal to Q and Q pi by 4 d square, where Q is nothing but the sigma v at the base of the pipe. So here it is 52560, and Q is given for 38 degree is 80. So put all this value Q and Q pi by 40 square and get tip resistance, tip capacity. After that, add friction capacity and tip and bearing capacity, get the ultimate bearing capacity of the pile, ultimate capacity of the pile. Then, for find out the safe ultimate capacity or design capacity, we have to divide this by factor of safety. We take factor of safety as 2, so divide this ultimate capacity uh, with 2 and get the answer. Now, same problem we use for the we use when there is a presence of groundwater table, and it is said the groundwater table is at a distance from the ground surface 10 feet. So there is a change in the pressure diagram. So you see that the pressure diagram changes due to this groundwater table. Uh, Again, we have to find out the if critical depth. Critical depth we have again 20 foot. Then now we have to find out the area of this pressure diagram according to the water table effect. Due to the water table, there is a decrease in the pressure diagram, or shape is distorted. So it is above, then we have to modify our diagram above the water table one part, then up from water table to up to critical depth is one part, and then from critical depth to base of the foundation is another part. So according to this, we find out the pressure, vertical find out the vertical pressure. So this is one triangle. From here it to here it is a trapezoidal shape. So we have to find out this. Then here to here it is a rectangular shape. So we see that the area of this diagram is half. First part is half 1280 into 10. Here to here distance is 10. Base is 1280. Then use the half trapezoidal equation, half 1280 plus 1936, and distance is again 10. Then bottom part is a rectangular, so you use 1966 into 5. And again this uh, is for find out the average effective stress. We have to multiply it with active earth pressure coefficient, and then 10 delta and pi d, uh, with the pi into d. So after that we get the answer is as 3.2 K, KIPS. Then again we have to find out the tip resistance, that is n bearing, which is equal to the q n cube by pi by 4 d square. So put all these value. Here q is 1936 due to the presence of water table. It is changes at the bottom of the file. So answer is 1 to 1.6 kp. So put all this, add to friction and n bearing, get the ultimate capacity, and if we divide it by factor of safety, get the safe design capacity of the pipe. Now try to solve one problem for uh, clay nature of the soil. So if this same problem uh, is used for the clay type of soil, but the pile length is here is given 35 feet, and the soil properties are given. Q is, that means 100 compressive strength is given. We know that half of the 100 compressive strength is equal to the 100 cohesion of the soil. So easily we get the C. Then gamma is given 140, and soil is clay, and length of the soil pile is 35. So in clay soil there is no need to find out the critical depth. So we use alpha C S surface. Uh, the formula is alpha into C pi dl, plus CNC pi by 4 t square, where NC is the 9, alpha is here given zero point 0.9, and put all this value in this equation and easily get the answer. So it is easier than this clay equations are easier than the to find out the capacity in clay is easier than find out the capacity in sand, because in capacity sand we have to consider the critical depth, pressure diagram, from which we find out the average effective stress. So now we solve some problem regarding to the pile group capacity. This just follow one or two reputed books. I am following here VNS Mutri or some writer, or I am taking these books from Sharp Profile. These details are also provided in Sharp Profile. Please go through it. I am taking Chang books, so please go through once. Very important books. These two are very important books. Now I am solve one problem on group capacity. So pile group, actually there is a single pile we don't use in pile foundation. We use as a group of minimum two or three piles. So due to the group, if you see that around the surface surrounding there is a creation of pressure pile or distribution of the pressure due to the pile. If you use this group, this pressure bulb is overlap each other, which is reduce the efficiency of the group. So we have to design in such a way that this pressure drainer should not overlap each other to get the maximum capacity of the pile group. And for this we have to maintain minimum spacing of the pile, and which is mostly used 2.5 times of diameter of the pile. The spacing is mostly used 2.2 to 3, 2.5 to 3 times of diameter of the pile. And these are the different types of arrangement of the pile foundation in group. So if you use three piles, these are the arrangement. If you use four piles, these are the arrangement with 5, 6, 7, 8, 9, and more on up to 12. Inheritance from up to 12. Now efficiency, there is one formula given by converse lever, which is depend on the number of pile along the row and number of pile in the column and the pile foundation, and also the angle, which is equal to the tan inverse d by s. D is the diameter of the pile, s is the spacing of the pile. So this follow, which is if you uh, the term, if you use in exam the term converse lever, then the formula is there. If asked to find out the efficiency for by converse lever equation, so the formula is 1 minus theta n minus 1 m plus 1 minus m into n divided by 90 into mm. Now in pile we have to find out two ways. In pile foundation we have to find out uh, the capacity of the pile foundation in two ways, either in block failure, that means the whole pile group act as a block and try to settle a failure in a single unit, and another way is to find out the individual capacity of the pile and multiply with the number of piles, and from this which is minimum we have to choose. So here it is given pile in cohesive soil. These are the formula for cohesive soil for block failure, and this is the formula for individual pile and multiply the number of piles. Now there is one problem given regarding to this, which pile group in clay. So I am just discussing this formula, which is very important for your problem, exam. So we said that a group of 9 piles with 3 piles in a row driven. into a soft clay, extending from the ground level to a great depth. The diameter and the length of the pile were 30 centimeter and 10 meter. Respectively, the unconfined compressive strength of the clay is given 70 kPa, and if the pile is placed 90 centimeter center to center uh, spacing, compute the allowable load on pile group basis of shear failure criteria for the factor of safety 2.5. So we have to find out for block failure and also find out for individual pile failure. So the block failure, the formula is CNC AG. AG is the surface area of the block. Uh, sorry, CNC AG. AG is the cross sectional area of the block, and PL C bar, where PG is the perimeter of the block. L is the length of the pile foundation in block. Then C bar is the average cohesion along the block. So here NC is the 9, C bar and C is same, which is equal to the 70 by 2, because here it is given unconfined compressive strength 70. So cohesion is half of this unconfined compressive strength, so it is 35. AG is the area of the cross section area of the block. So here it is given 3 by 3 piles. So and the center to center spacing is given 90 centimeter, which is zero point 0.9 meter. So 3 into, so so the spacing is in between. So the area is, sorry, length of the length and width of this block is 21 2.1 meter by 2.1 meter, because it is n minus, the formula is n minus 1 into spacing plus d. D is the diameter of the pipe. So n is here 3, minus 1 is 2. 2 into spacing is zero point 0.9. So it is 1.8 plus diameter of the pipe, it is zero point 0.3, which is further equal to 2.1. And perimeter of the block is 4 times of the, it is a square pile group. So it is 4 times of the length of the pile group or block, which is equal to the 8.4 into 2.1, which is 8.4 meter. So put all this value in this equation and get the answer, and it is given 1730 kilonewton, uh, which is a safe ultimate capacity of this block failure by dividing by the factor safety 2.5. And now we have to find out this for individual pile. And individual pile, the formula is similar. I use alpha for addition factor, and alpha value is given by assume 1. So put all this value, formula is Q, uh, or we can say CNC pi by 4 plus alpha C pi dl. So n is here 9, C is here 35, pi d is here zero point 0.3, L is here 10. So put all this value, alpha we assume 1, put all this value, and it is given for single pi. It is 352 kilonewton, but there is a 9 numbers of pi. So the answer is 1267 kilonewton. So along from above, we see that the minimum value is given by the single individual pile. So our capacity of this pile group is 1267 kilonewton. Now settlement of the pile group, we study it in our previous classes. Now we try to, so settlement of the pile cohesive soil, we see that we have to calculate the load distribution from the ground surface at a distance of two-thirds of length of the pile from the pile cap. And if the soil is, this is for the uh, soft clay, the homogeneous clay. If there is two layers is present, one is weaker layer and another is a firm stratum below the base of the pile foundation, then we use the pressure distribution from the base of the pile foundation. So you go through this type of diagram to solve the settlement of the pile foundation. So here one, you go through it. This is a big problem. This is a very important problem for you exam purpose. So now in SC, one problem is given. It is required to construct the pile foundation comprised of 20 piles arranged in 5 columns. That means 5 by 4 arrangement at a distance of 90 centimeters center to center. Then diameter of piles is given 30 centimeter. Length of the pile is given 9 meter. The bottom of the pile cap is located at a depth of 2 meter from the ground surface. The details of the soil properties are given below, and the water table was found at a depth of 4 meter from the ground surface. So it is very critical, a complex problem. So here first we have to draw the soil according to the given data, layered soil according to the given data. I think it is drawn. So so first we find out the shape, that means length and width of the pile cap, so which is equal to uh, you see that we assume the total load is 250 kilonewton and it is act as a depth, we know that it act at a depth of uh, two-thirds of the length of the pile from the base of the pile foundation, also pile cap. So and from the bottom, width of the pile cap is 2 meter. So the at the surface it is at a distance of 6 plus 2, 8 meter below the from the ground level, and water to be present at a 4 meter depth from the ground level, and the size of the footing is given as pile cap is given 3.9 to 3 meter, because how it is came in same formula n minus 1 into s plus d. So here n is 5, so 5 minus 1 4, 4 into zero point 0.9, that is 36 3.6 plus zero point 0.3 3.9, and for um, this is length. For width it is n minus 1, that means 4 minus 1 into 9, that is 3 into zero point 0.9, it is 2.7 plus zero point 0.3, it is 3 meter. Then we divide the according to the layer. So from we have to calculate our settlement from 8 meter depth. So there from according to the question, we have to divide the in layer. So there is three layer. One is from 8 meter to 12 meter, that is 4 mm thick. Another one is 2 meter, the 12 meter to 14 meter, that is 2 meter thick. Then uh, 40 meter to 70 meter, that means 3 meter thick. So for each layer we have to find out the consolidation settlement. So we use the consolidation settlement formula H is by 1 plus E naught into log sigma V plus del P. divided by del sigma by sigma v. Sigma v is the effective stress. Here it is given P naught, and del P is the increased pressure due to the construction increase of pressure at the middle of the clay layer due to the increase of the construction of the pile foundation. And this is given for this we use the load stress question method as 2:1 method. So first we find out the sigma v, that is here PV at a different depth at the middle of the different layer. So by effective stress formula, considering the water table at a depth of 4 meter, and then we have to find out the del P and each layer middle of the each layer. So use 2:1 method. So after that, using this formula, for each layer E given, CC given, so put all these value, get S1, S2, S3. After that, plus sum up and get the total settlement, which is approximately equal to 160 mm or 16 centimeter. Now we try to solve or discuss about the sheet piling or anchor piling, which is the advanced type of the foundation and deep foundation. Stay on the line. So, so please give me 2 minutes. I will come back. So sheet piles are retaining walls constructed to the retain structure, water, or any other fill material, and the general use of this sheet pile are for waterfront structure, example in built-in wharf, quays, and piers, and also for building diversion dams such as coffer dams, riverbank protection. We use sheet pile. Regarding the sides of carts made in earth, we use sheet piles. Then these are the different types of sheet pile arrangement. You see that straight sheet piling, shallow, arc, this web piling, arc web piling, Z pile like that. Now this sheet pile possesses several advantages over the other type. We can see that resistance to high driving stresses and as developed in hard or rocky material. They are lighter in section. They may be used several times. Also, they may be used either below or above the water and possess the long life, suitable joints which do not deform during the driving can be provided to have continuous work. The pile length can be increased either by welding or bolting. These are the advantage of the sheet pile. Then there is a different types of sheet pile, anchor, cantilever sheet pile, anchor, bulkhead sheet pile, brace sheet piling in cars, uh, single cell coffer dam sheet pile, cellular coffer dam, circular type, cellular coffer dam, diaphragm. Now these are the different arrangement or types of the sheet file. In this figure, we can go through it. So now we have to find out. We discussed in earlier the pressure diagram is associated with this sheet file. So this diagram, this line is the sheet file, a deep dark line, and it is rotated about a point O due to the earth pressure acting in both the side. Here, the right side it is acting the active earth pressure, and the left side is acting the passive earth pressure. But after at the bottom of the zero or point of rotation, this is opposite. At the left side is acting active earth pressure, and the right side is acting passive earth pressure. So these are the pressure diagram of this sheet pile. We see that the pile active pressure after a point O, this is shift to the passive earth pressure. Again after O dash, it is again shift to the passive earth pressure. So we have to design the sheet pile to find out the embedment depth, that is capital D. So all of these this diagram arrangement we need to find out our capacity. So these are the formula. You can go through it. It is to find out the capacity of embedment depth. So after that, at last we find out the depth of embedment equation, which is in fourth order, which is very difficult to solve. So for also find out the maximum bending moment. Now for this critical, because this pressure diagram is very critical and very complex. So for this we simplified this pressure diagram. So we consider that the left side is act passive earth pressure, the right side only act the active earth pressure. And also this is due to the distribution of this pressure, the act of the location of the pressure force we also identify from the base of the foundation, and we easily by this pressure diagram we easily find out the depth of the momentum depth, that is D, which is from measure from dredge level. So here it is the formula K d cube minus 3hd into h plus d into Ka is equal to 0, where K is the Kp minus Ka. So in this equation it is very simpler from the previous equation because it is in third order, previous one is fourth order. So most of the case design, approximate design, we use this equation. And after that, we increase this investment depth for safety 20% to 40%. So now, if, if the previous one is for without water table, now what happen if there is the presence of water table? So you see that everything is same, but the pressure diagram it is little bit changed due to the presence of water table because we use the gamma dash in place of gamma. Gamma dash is nothing but the submerged unit rate of the soil, which is equal to the gamma saturated minus gamma W. Now everything is same, only gamma is replaced by the gamma dash. So now there is the one problem we have to solve in sophisticated manner. So it says they determine the depth of enrichment of the sheet pile. From the example, figure is given in below this figure. Now, and by rigorous analysis, it is already said rigorous analysis. I think in your exam it is come a simplified method. Uh, it is because it is very simple way to define. But here only given sophisticated or rigorous method. So I'll go through it. So I'm discussing. And given that the minimum sectional modulus, determine also minimum sectional modulus, allowable flexural stress is given, and also effective unit weight of soil is given, friction, internal friction also, angle of internal friction also given, 30 degree. So first to find out the Kp and Ka. After finding out the Kp by using the relevant formulas, then after finding the Kp, Pa bar is find out which is equal to the gamma H K. After that, find out the Y naught. Y naught is the distance from the dredge level to the point of rotation, which is equal to the P bar divided by gamma into Kp minus K, or we can say only K. After that, we have to find out the total passive force acting, which is equal to the half of Pa bar into H plus half of Pa bar into Y naught. After that, we have to find out the average uh, passive pressure, which is equal to the gamma D Kp minus Ka minus Pa bar. After that, which is come in terms of D, because we don't know the D value of, that means depth of embedment. We have to find out the depth of embedment. After that, we have to find out the P dash bar, which is equal to the gamma H Kp plus gamma D Kp minus Ka. Again, this is come in terms of D. Then at last we have to find out the PP a double dash bar, which is equal to the gamma H Kp plus gamma Y naught Kp minus Ka, which is comes 340 kilonewton. Then we have to find out the Y bar. Y bar is the distance from the dredge level to the point above the dredge level to the point where the total passive earth pressure is. So active earth pressure force is acting, which is equal to for this we use Pa y bar is equal to half of, that means we equating the moment both side, that is half of Pa bar h by 3 plus y naught, which is in bracket, plus half of Pa bar y naught in bracket, two-third of y naught. So now if we put all this value in this equation, we get First we get the y bar. Now if we put all this value in this equation, d naught to the power 4 plus c1 d naught cube plus c2 d naught square plus c3 d naught plus c4, where c1 is pp double dash bar by k gamma k, where c2 is 8 pa minus 8 pa gamma k, c3 is minus 6 pa gamma k whole square into 2 y bar gamma k plus pp double dash bar, and C4 is the minus 6 Pa y bar PP double dash plus 4 Pa square divided by gamma K whole square. So after putting all this equation is come in terms of D and solve the value of D, fourth order equation. We use scientific calculator to solve this fourth order equation. After that, if you add D naught with why not? We give the total abatement rate. For safety purpose, we use increase this D by 40%, which that is 1.4 times. So it is 8.5. So our in designing case, the depth of the abatement depth of the sheet pile is 8.5. Now here it is find out the sectional modulus. So for this using this formula, which is equal to the y naught bar is equal to root over 2 pa divided by gamma k. After that, you will find the maximum moment. It is pa into gamma bar plus y naught minus half 1 by 6 gamma naught bar cube uh, gamma k, and find after that find out the section modulus. Now move on to the anchor sheet pile. Cohesive soil also we can find this sheet file. We go through it. So higher. So anchor bulkhead or anchor sheet pile, and it is mostly if these are mostly used in granular soil. So if the sheet pile uh, have been driven in a shallow depth and deflection of the bulkhead is somewhat similar to the vertical elastic beam, and lower end is be simply supported and another end is fixed as shown in figure. The bulkhead which satisfy the condition called bulkhead with free earth support, and we see that. So these are the elements. One sheet pile is driven and this sheet pile is attached with a rod or something which or anchored somewhere that which is with a fixed support, which is driven in a solid soil to remove the failure, and this arrangement is called the anchor sheet pile or anchor bulkhead. And here in this anchorage will act the tension force which is help to create some stability against rotation of this sheet pile. These are the equations to find out these forces. You see that this is dash level, this is deflected shape. Previous this deflection shape is air from the uh, backfill material. Now it is in the backfill material, and this is the failure surface or wedge passive wedge surface. And here it is the pressure diagram. So which is very important to solve the find out the embankment depth and solve the effective stress, passive earth pressure and active earth pressure, and it's a bending moment. So regarding this, there is a one problem. You kindly go through it, and I am not discussing this now. At last, here is the problem. Very simple problem. Just remember the formulas for different steps, and it is very simple from the sheet file also. Just remember it and the formulas and apply it and directly get the answer. Now we discuss a little bit about the uh, struts, brace cuts or struts, which is used in deep excavation, which is help to support the earth and surrounding soil in the excavation. And the struts is arranged in this way with the help of sheet piles and also with the help of H piles. So these are the arrangement of the base cut or star, which you will see that it is used to support the earth laterally. And to analyze these joints we consider as a pin joint. So based on this, we analyze. So we see that due to the pin joint, the moment is not distributed from here to here. Only vertical force are distributed. So we have to find out the force on this start. So for this we have to divide this start according to the number of the pin joint and find out the pressure. And here we see in the last it is given the different types of pressure diagram act along this rigid curve. For sand it is uniform and the width of this pressure diagram is 6.5 gamma h 10 square 45 degree minus 5 by 2. And for stiff fissure clay, the pressure diagram is trapezoidal shape. So and that means it is increasing first, then it is remain constant. After a certain depth, it is decreasing. The depth from the surface it is 0.25 h, where it is increasing. So at a distance point at, at the middle depth is 0.5 h, which where pressure is remain constant. At last it is 0.25 h, where again pressure is decreasing, and the width is of the pressure diagram is in between zero point 0.2 gamma h to zero point 0.4 gamma h. Then there is the soft to medium clay pressure diagram. So for this, the pressure diagram is first increasing, then remain constant. So the increasing depth is 0.25 h. After that, it is remain constant, and the width is gamma h minus 4 into c. C is the quotient of the soil. Gamma is the unit weight, h is the height of the this excavation. So based on this diagram, we have to solve or we solved some problem in previous classes. Please go through it. It is very easily we solve this question. No need to discuss here again. So I think we already cover almost all the things in this lectures series. So I think we covered almost all the things of this foundation engineering class. So we are at the end of this wonderful journey. So I think whatever I am discussing, it is very easy to understandable to everyone, and I am also covered most of the numerical problems also previous year also, and discussing how to solve the assignment problem this year also. Please go through it and prepare by yourself for the exam, which is coming on in few days. After few days, so please be prepare yourself for this exam. Very, please go through all the slides at once first. After that, try to solve the previous year question which I am sending to you by yourself first. If problem arises, go through the solution, then solve the question again. And there is two or three topics are very important. Like first is shallow foundation. What are the different types of foundation and their bearing capacity equation? Then settlement of the shallow foundation is very important. Then earth pressure theories is very important for your exam. Then pile foundation and pile group capacity is very important. At last, sheet pile also very important. Brace cut is very important. Then dynamics of the foundation also very important. So please go through these topics very rigorously and try to solve the question more on these reputed books. I am preferring you to follow the uh, VNS Murthy book, which is very wonderful book, and also Bajra Das, Principle of Soil Foundation, Foundation Engineering, Principle of Foundation Engineering, Bajra Das, which is also very good book. So you go through these two books, which is good for your exam purpose, the preparation of exam purpose. Now I am stop here. If uh, if you take if I am taking this course again, I think we will meet again. Uh, or I think if I am taking Nptel course, we will meet in another course also. So till then, thank you everyone. I am stop here. So best of luck to your exam and to your future. And prepare by yourself. This is our last class. So I am stopping here. Good luck to everyone. Thank you. Thank you very much. It is a wonderful journey. So thank you everyone. Thank you. I am stopped here.